Hello everyone, welcome back to our NDT training session. I am Muthulakshmi, ASNT Level 3 in 10 methods, API, PMP and Frozio Level 3 certification holder. And it's great to continue our journey into the world of non-destructive testing. In our previous session, we extensively discussed magnetic particles and their properties in magnetic particle testing. Now we are going to dive deep into the fundamental techniques and equipment used in this critical NDT method. Let's start the session. First, we discussed about magnetization techniques in magnetic particle testing. Let's start by understanding how we magnetize our test objects. There are two primary categories. First one is permanent magnets. Second one is electromagnets and electric current. First, we discuss about permanent magnets. These are the least flexible options. They are always magnetized, which can make them difficult to handle, especially with large objects. Crucially, magnetization cannot be turned off once applied. This constant magnetic field can sometimes interfere with other inspection steps or make it challenging to remove residual magnetism. This is the permanent magnets. The next one is electromagnets and electric current. These are most commonly used in magnetic particle testing. They offer controlled magnetization, allowing us to adjust the field strength as needed. The key advantage is the ability to enable on-off switching for testing convenience. This allows for a more controlled inspection process. Next topic is magnetization by electric current. When we use electric current for magnetization, the test object effectively becomes part of magnetic circuit. A magnetic field is induced within or around the object by passing current through coils or directly through the object itself. This is the coil, through the coil or directly into the object. This is our object. Next, we see an extremely important concept in magnetic particle testing is directional sensitivity. This is most important concept. Maximum sensitivity is achieved when the magnetic flux lines are perpendicular to the discontinuity. Imagine trying to disrupt a straight line with a parallel crack. It's hard to see, but if the crack is perpendicular, it cuts across the lines, creating a significant leakage field. Imagine this is our object. Here, one surface crack. We using the longitudinal magnetization. So, our magnetic flux lines are move north to south. Here leakage fields are created. So now flux line is perpendicular to the discontinuity. So we can easily identify the defect. Next, because the flaw orientation is usually unknown, it's standard practice to perform testing in two perpendicular directions. This ensures that you can detect discontinuities regardless of their alignments. To help with this, a grid may be drawn on the surface of the test object to guide dual direction testing. This is a very important topic in magnetic testing. It ensures through coverage and detection. Let's move on the next slide. Magnetizing coil in magnetic particle testing. A common method for inducing a magnetic field is using a magnetizing coil. Encircling coil and magnetic field. A magnetizing coil is simply a coil of wire used to encircle the test object. To determine the direction of magnetic field generated by the coil, we use the right hand rule. Already we saw a previous video. If your thumb points in the direction of the current flow through the coil windings, your fingers will curl in the direction of the circular magnetic field around the conductor. So this is the right hand rule. Next one is field line behavior. Without a test object inside, the magnetic field lines from closed loops around the conductor. The magnetic field strength generated by a coil is influenced by several factors. First one is current through the coil, second one is number of coil turns, and third one is the geometry of the setup. Next topic is field measurement. In many common configurations, field values are pre-established. However, in practical applications, we use Teslometers with Hall elements to accurately measure the magnetic field strength. This ensures we are applying the correct amount of magnetization for effective inspection. This figure demonstrates how a test object is magnetized using an encircling coil with direct current. So, encircling current coils. A rod magnetized longitudinally using a direct current encircling coil. Discontinuities like P and Q cause flux leakage, which is where magnetic particles will cluster. R and S help monitor field intensity and flux density, ensuring the part is properly magnetized for effective magnetic particle testing. Here how the magnetization works. First, direct current pass through the coil. This is coil. So, direct current passes through the coil. The current induces longitudinal magnetic flux in the rod aligned with its axis. Defect detection. Surface and near surface flaws perpendicular to the flux cause flux leakage, which can be detected using magnetic particles. These are the flux lines. Now you all understand? Let me move the next slide. Testing in active and residual fields, magnetizing coil using. We can apply magnetic particles and observe indications in two main ways when using a coil. First one is testing in active field, second one is testing in residual field. First we discuss about testing in active field. In this method, probes or the inspector scan the object during the application of magnetic field. The current is still flowing, then small fields are generally sufficient to detect surface breaking or transversely oriented discontinuities. These are often the easiest to find. However, larger fields are needed for subsurface or internal tube defects. These flaws are harder to detect as the leakage field is weaker at the surface. Optimization is crucial because the inspector must adjust the field strength for the specific discontinuity type they are trying to find. Too little field and you miss defects. Too much and you can get false indication or saturation. Next one is testing in a residual field. With this technique, the object is passed through the coil and the current is then turned off. The magnetic particles are applied after the current is off, relying on the residual magnetism left in the material. This method is suitable for materials that retain a significant amount of magnetism. To achieve maximum field exposure during magnetization, the coil should be elongated and the test object should be placed near its inner surface. Next, a significant risk here is oversaturation, which can cause the particles to stand up, creating a fur effect, especially at the ends of the object. This makes it difficult to interpret true indications. The ideal condition for residual field testing is a slightly undersaturated test objects, which generally yields better results by preventing the fur effect. The field strength must always be optimized based on the object's geometry. This is the testing in residual field. Let's move on the next slide. Applied direct current and capacitor discharge devices. Beyond coils, direct current and specialized devices are used for specific magnetization types. First one is applied direct current. DC magnetization is ideal for objects like bars, billets and tubes. For optimal detection, you need to adjust the current flow orientation so that discontinuities interpret the current path. This maximizes the local flux leakage. Circular magnetization is a common application of DC and can be achieved in two ways. First one is by passing direct current directly through the tubular objects. Next one is or by using a central conductor through which DC is passed, creating circular magnetic fields around it. We can identify these images. This is DC directly through the tubular objects. These are the flux lines. This is the central conductor through which DC is passed. Here circular magnetic fields creates. So next, capacitor discharge devices. These devices are specifically used for circular magnetization of tubes or longitudinal magnetization of objects' ends. A typical system consists of a capacitor bank charged to a specific voltage and a discharge path through rod or cable and SCR. SCR means silicon controlled rectifier with resistance R. This is shown figure 34. An important design consideration. A larger capacitance at a lower voltage will produce a longer pulse duration. This longer pulse helps to reduce the eddy current losses and it improves magnetization efficiency. What is the safety note? For outdoor use, the voltage should be limited only for 50 voltage to ensure operator safety. In the first configuration, a conductor passes through the center of the hollow test object. When the capacitor discharges, the discharge current IC flows through the conductor. This induces eddy current IE in the wall of the part. This induces eddy current. The magnetic field forms in circular loops around the conductor, creating a circular magnetic field. So this is best for detecting longitudinal cracks. This is the crack along the surface because the field is perpendicular to them. This is a part A. In the second configuration, a flexible cable, this is a flexible cable, is wrapped around the outside of the test object like coil. This is our test object. When the capacitor discharges, the current pulse IC flows through the cable. This creates a longitudinal magnetic field running along the length of the part. So this is for detecting transverse crack. This is the transverse crack because the field lines run along the part and cracks perpendicular to the flux cause leakage. Let's move on the next slide. Magnitudes of magnetic flux leakage fields. Understanding the strength of magnetic flux leakage fields is critical for probe selection and inspection sensitivity. First one is magnetic flux leakage, MFL intensity. In the active field, the typical applied internal field is between 3.2 to 4.0 kA per meter. The resulting leakage peaks are generally in the range of tens of millitesla, hundreds of Gauss. These are relatively strong and easier to detect. Next one is in residual field testing, the leakage fields are much weaker, often only hundreds of microtesla. This makes detection more challenging and requires more sensitive probes. Interestingly, there can be possible field reversal depending on the initial excitation and the size of the flaw. The next one is optimal operating point. At low magnetization, the magnetic flux lines tend to bypass the discontinuity without creating significant surface leakage. You simply won't see the flaw. Next one is as magnetization increases, the material's permeability decreases. At this point, the leakage begins at the surface because the steel can no longer redirect the flux tightly around the discontinuity. With an even higher applied field, the permeability continues to drop and flux leakage becomes prominent. This not only helps detect discontinuities but also reduces surface noise, making the indications clearly. The next one is residual field testing tip. For effective residual field testing, it is crucial to ensure the material is fully saturated before switching off the current. This ensures maximum residual magnetism. Keep in mind that once the current is removed, the field decays immediately. So the timing of particle application is residual methods is important. In this picture, this is very important in magnetic particle testing because flux leakage behavior directly affects defect visibility. In part A, the material is magnetized at low level of induction. The magnetic flux lines through the part and around the discontinuity, the lines compress slightly. So here slightly varied and stay mostly inside the material. Here in the surface, no fluctuations. No surface flux leakage occurs. So a crack or void at this stage may not be visible with magnetic particles. So low magnetization means flux lines stay internal, no flux leakage and flaws may go undetected. This is a part A. Next one is part B. This is high induction. Flux leakage occurs. The material is magnetized at high level, approaching or reaching saturation. The magnetic flux lines are no longer compressed enough to remain completely inside the material. At the discontinuity, flux lines leak out the surface. This is the surface. This is the leakage. So creating a magnetic leakage field. This leakage attracts the magnetic particles, forming a visible indication of the flaw. So high magnetization, surface flux leakage, flaw becomes visible during the testing. So we move the next slide. Magnetic test probes in magnetic particle testing. Magnetic probes are our eyes and ears in detecting the invisible flux leakage testing. Purpose of magnetic probes. Their primary purpose is to detect and quantify the magnetic flux leakage fields caused by discontinuities. These leakage fields are localized around the flaw and can be resolved into three components. First one is normal, tangential, axial components. Probes are specifically oriented to detect specific field components. Example, a probe designed for normal flux will be less effective for tangential flux. In this section, we are looking at figure 36, which demonstrates how the orientation of a pickup coil affects its sensitivity to magnetic flux density components. First part A, coil sensitive to normal component. The pickup coil is placed horizontally. So this is horizontally placed parallel to the surface of this is the surface of the test object. This orientation makes the coil sensitive to the normal component of the magnetic field. It means it primarily detects magnetic flux that is perpendicular to the coil's plane or normal to the surface. This setup is effective for measuring leakage flux emerging vertically from surface cracks or defects. Part B is the pickup coil is rotated vertically, standing perpendicular to the surface of the test objects. This makes the coil sensitive to tangential component of the magnetic flux. It means it primarily detects flux lines running parallel to the surface of the material. It is useful for detecting flux variations along the surface and for mapping magnetization distribution. Let's move the next slide. Probe types. First one is pickup coils. These are small air or ferrite core coils. They measure the rate of change of flux through the coil axis. This means they are sensitive to movement. You need to scan them. They are orientation sensitive and can be aligned to detect a desired field component. Their output depends on the probe velocity, which must be constant for reliable readings, and the gradient of the flux. Next, the output signal can be integrated to measure the actual flux density. Sensitivity can be enhanced by using ferrite cores. Next, magnetodiodes. These are very small and highly sensitive. They are more effective for detecting angled or small discontinuities. However, they are less effective than coils for large flaws. Next is Hall effect detectors. Widely used to measure flux leakage in Tesla. Then they function by detecting a voltage that is generated when a magnetic field is perpendicular to a current flow within the Hall element. So this is within the Hall element. Next one is Geont magnetoresistive probes. These have a unique structure consisting of magnetic layers separated by non-magnetic layer. Their electrical resistance changes significantly with an external magnetic field. They offer high sensitivity and are particularly useful for detecting low-level leakage fields. However, their response decreases with increased field strength, meaning they are best suited for weaker fields. Next is magnetic tape. This is a unique method for primarily used on flat surfaces. A special tape records the leakage field, which is then scanned later with probes. The tape is reusable after erasing the recorded field. It must be handled carefully, as a physical damage like scabs, silvers can tear it. Next, the magnetic particles in magnetic particle testing and imaging. Finally, the star of the show, the magnetic particles themselves and how we visualize their indications. First, the purpose and principle. Magnetic particles are widely used to form visible indications of discontinuities. This is the most important point. Then the principle is very simple. These particles accumulate at the leakage fields caused by the disruption of magnetic flux near flaws. These indications become visible to the naked eye or through cameras. Their visibility is often enhanced using reflective or fluorescent pigments. It's crucial that the illumination means visible light or UV light, matches the pigment type for proper detection. Next one is application techniques. First one is dry testing, second one is wet testing. Dry testing uses larger particle size, means 50 to 180 micrometers. Best for large surface flaws such as those found in welds or castings. Particles are applied as a cloud or stream. These particles are also coated with reflective or fluorescent pigments. Next one is wet testing. Uses much finer particle size, typically 5 to 20 micrometers, ideal for the detection of fine cracks. Particles are suspended in a liquid carrier such as oil or water, applied via spray or immersion of the part. Also utilizes reflective or fluorescent pigments for enhanced visibility. The next one is imaging magnetic indications, flying spot scanners. These systems use a laser or a narrow beam of light to excite the magnetic particles. Only the light emitted from the particles other to a flaw is detected. This helps to minimize background noise. They utilize a phototube combined with a filter specifically for fluorescent light detection. The detected signal is then amplified, digitized and processed by a computer for analysis. Next is charge coupled devices, CCD. CCD cameras are used flood lighting to excite the particles over a wider area. The CCD camera captures the light emitted from the particles using optical filters. Each pixel in the CCD array stores a charge based on the number of photons it receives. Photons based charge. These charges are then read out via a shift register and converted into a video signal. CCD systems are often interfaced with frame grabbers and image processing software which can perform advanced functions like contrast enhancement, edge highlighting, noise reduction. These features significantly improve the visibility and interpretation of flaw indications. This is the final stage of our session. I will prepare some questions for this session. Comment your answers in the comment box. I hope this concept is now clear to everyone. If you have any further clarification, please drop them in comment box. Thank you.